All right. You can go ahead and take it away.
Perfect. All right. Welcome, everybody. I would like to begin by thanking Sebastian Bay and the organizers of this event for inviting me over to my first talk at GUWS, and of course, everybody else for taking the time to attend. Today, I would like to present some of my PhD work on wargaming as a tool for historical analysis. And I'd like to begin with a very quick introduction about myself. I'm a school teacher in a school in Madrid, and it is September, so please excuse the scruffy and disheveled appearance. It's been a rough couple of weeks. More directly related to wargaming, I'm a PhD candidate at IUGM, which is a Spanish institute attached to the Ministry of Defense. And I co-edited a book on Royal Navy wargaming with Dr. John Carey, the cover of which you can see on the screen. Dr. Carey did most of the heavy lifting on that one, while I focused on the Royal Navy's 1929 war game rules. But still, it felt really nice to see my name next to his on a book cover. I have presented at various wargaming events in Spain and Portugal, and recently at VCAO, the virtual conference of wargamers organized by Wargame Developments. You will hear today much of what I told them then, but I have made some additions in case there are any repeat customers, which it's likely, let's face it, because I'm painfully aware there's only so many naval wargamers out there. In today's talk, I will explain the methodology that I propose in my work, and I will present 3 case studies from 3 cruiser actions of the First World War. And we'll begin with a few passing remarks on the Battle of the Denmark Strait, which you will probably have observed is 1, not a cruiser engagement, and 2, not from the Great War. The reason that I bring it up is that a now defunct wargame publisher called Omega Games of Ranger fame published 2 tactical naval games about 4 decades ago, which looked like your standard hex and counter fare with a couple of twists, like a fleet morale system, so battles did not devolve into a slugfest of mutual annihilation. But as you read the rules, it became readily apparent that it was a game that revolved around one very specific design concept, and that was the concept of the immune zone, which, as shown in the current slide, is a range band in which we're far enough away from the enemy to be safe from penetration of our vertical armor, of our belt armor, but not so far that deck penetration from plunging fire becomes a problem, so we're relatively safe. I would like to remind everybody, of course, that a non-penetrating hit from a 15-inch shell is very far from gentle, so perhaps the word immune is a bit misleading in the expression. At any rate, if you tried to fight the Battle of the Denmark Strait using the game and at the ranges historically reported, something funny happened. What happened was that the battle could not happen at all, because HMS Hood would have been in the immune zone from Bismarck's fire, and hence it would have been impossible for her to blow up in the game. Now, as you may imagine, this sparked a very heated discussion in Board Game Geek, and before long, the designer chimed in with words to the effect that the game was right, and it was the battle that was wrong. I have nothing but respect for that approach, and I admire a designer that is willing to die on a very specific hill. The quote is very dramatic, but what he actually meant was that a number of things might have happened. Maybe the ranges reported were wrong. Maybe there was a flaw in Hood's armor, and there was a fluke penetration. Or perhaps the explosion of HMS Hood was not caused by a penetrating shell hit at all. Maybe her aft magazine exploded for a different reason. And that's not a lunatic conclusion, in fact, and the debate is still ongoing. There's a fantastic article, I think it was from 1987 by Bill Urems, that I recommend that you read if you're interested in the fate of HMS Hood. But the fact is that everyone just expects Hood to blow up in a wargame simply because she did. And that's a bias that wargamers experience constantly, and historians even more so. David Hackett Fisher summarized it very well when he invited the readers of one of his volumes to imagine a letter written in France on May 24, 1337, stating, "The 100 Years' War began here today." He referred to that as the historian's fallacy, and it's true that historians are cursed with looking at things a posteriori. But that aside, they're often analyzing very complex processes with a myriad possible outcomes using a sample size of just one. We know, for instance, that a number of battlecruisers blew up at Jutland, but one wonders what we would see if we could be spectators to 100 Jutlands. And alas, we don't have 100 Jutlands to look at. We barely have the one, in fact. Norman Friedman pointed out very wisely that in spite of World War I being a primarily maritime war, relatively little action took place at sea. In fact, to offer some rough figures, John D. Granger, the author of the Dictionary of British Naval Battles, just to choose one volume, lists 28 Royal Navy surface encounters only between 1914 and 1918, of which only 16 involved cruisers and larger ships. 7 of those were single ship actions, and the remaining 9 were what we could call, somewhat grandiosely in some cases, fleet actions. And of those, only 4 and 5, respectively, resulted in the loss of at least one ship. The fleet actions that remain after weeding out the unlikely candidates are first Heligoland Bight, Coronel, the Falklands, Dogger Bank, and Jutland. And as for the cruiser actions, we have the destruction of Pegasus, that of Emden, that of Dresden, the first one, because they built another one later, and that of Königsberg. And since both Dresden and Königsberg were scuttled, our already very limited dataset is further polluted. In contrast, the US Army Concepts Analysis Agency has a database of land battles called CDB90, which has 123 entries for the same period. Now, I'm well aware that CDB90 is not the utmost authority on what a battle is or how many took place, but the comparison, if rough, should at least establish that naval historians normally have much fewer data points to work with. In fact, it would not be a stretch to say that we are dealing with evidence that a number of scientific disciplines would consider anecdotal at best. We may be able, if we're lucky, to ascertain what happened in a battle, but we have very little to compare our conclusions to, and certainly very little way of establishing trends that can help us determine if something was likely to happen or not. When a scientist is missing data points, there's 2 possible approaches to follow. One of them is experimentation, which in our case means we could just fight World War I all over again, and this time take very careful notes from the beginning. But that being wholly impractical, we can go for the second approach, which is simulation. The problem with that is that we need a very, very solid quantitative grounding to make a model that represents reality in any close way. And I think that's where wargaming and military operational research might come in handy. Everyone in the audience, I assume, is very familiar with wargaming, and I suppose you will agree with me that most, probably professional wargames are backed by some sort of painstakingly detailed simulation engine so that they can represent reality with some degree of fidelity. And this simulation engine is frequently supported by very ample operational research data. I have a picture on the screen right now of the 1826 edition of the Prussian Kriegspiel, designed by Lieutenant von Reiswitz the Younger, based on the work of his father. I believe it was Jorrit Vindies who gave a fantastic presentation on it on this same platform a while ago. And to come up with the firepower figures in the game, he and Gerhard von Scharnhorst spent quite some time conducting extensive tests at the firing range in Berlin. And then raw data is not everything. That's an edge that wargaming has over military operational research, and that is that the simulation data is frequently tempered by the experience of the umpire, of the people writing the rules, and even of the participants. In fact, I would go as far as saying that by reading the rules of the Prussian Kriegspiel and playing a game or two, one can get insights on how Napoleonic warfare happened that they would not be able to find in any other text. In our naval environment, we might refer to Lieutenant Castle's 1873 game titled A Game of Naval Tactics, for which he also very, very painstakingly documented the turning radiuses of every ship in the Royal Navy service at the time. There's a very good book by John Carey from 2014 talking about this game. And then we have efforts which are traditionally associated with military operational research, but were, funnily enough, wargaming efforts in their origin. I'm talking about Jehu Valentine Chase's pair of differential equations developed in 1902 to calculate the outcomes of Naval War College games. And he must have done something right, because we're told by Wayne Hughes Jr. that his work was classified until 1972. So his conclusions were interesting enough that they were worth keeping away from the eyes of a number of people. And famously, Frederick Lanchester, the British automotive engineer, and Mikhail Osipov independently developed the same equations. Some authors nowadays refer to these equations as the CLO equations, which stands for Chase, Lanchester, Osipov, so that all three get credit just the same. Chase's work was the inspiration for Wayne Hughes Jr.'s famous Salvo model. And then Bradley A. Fisk, also of the US Navy, wrote a prize essay in USNI proceedings titled American Naval Policy, in which he presented a rudimentary mathematical model of naval combat, and his work was essentially a tabulated version of the equations developed by Chase. All this basically goes to show that there was an effort at the turn of the century to look at naval warfare much more rigorously than before. The early 20th century naval games were very highly scientific devices, and they made very conscious efforts and very serious attempts to get everything right. I cannot continue talking about this without referring to Toby Ewing, who has done fantastic pioneering research work in the pre-war Royal Navy Games. And his work is a joy to read. So if you have the chance of reading what he has written, you're going to find it an education, as I did. It's very interesting to see how the Royal Navy and the US Navy already had slightly different styles in their adjudication. The Royal Navy had a tendency towards leaning on the umpire to adjudicate everything, whereas the US Navy tended to writing everything down. I firmly believe that this is due to the influence of McCarthy Little as he worked to turn the Naval War College into a proper academic community in which everybody had a voice, not just the experienced officers. But the point of the matter, at least for us, is that they were more than just games. And in fact, for historians and analysts, the games are living documents that can give us a very comprehensive view of the military wisdom of the era. And the assumptions that they make were not just educated guesses. They were concerted efforts to deal with the subject in a very serious manner. The key concept that I would like everyone to take away for the rest of the talk is that the games represent the mean expected outcome of potential conflicts that officers of the 1920s would expect to see based on their experience from the First World War. So the methodology that I propose is using this mean expected outcome as a yardstick to measure how the battles actually played out. In a sentence that I'm very proud of, because it sounds much smarter than it actually is, rather than use history to validate the model, I think we can use the model to validate history. Essentially, we run the engagements using the games as a simulation, and we compare the model output to the historical outcome. And with that, we can answer a few questions. Were the engagements typical in any way, in the sense that they matched what officers of the era would have expected? Or were they anomalous? And if they were anomalous, how and by how much did they diverge from expectation? And can we pinpoint the reasons for this divergence? Now, the great thing about this is that, if nothing else, it's a way of thinking about the battle in more scientific terms. It's a mental exercise, and we have a quantitative anchor to keep us from straying too far from our intended objective. The first game we'll be talking about is the Royal Navy 1921 game, titled Instructions for Strategical and Tactical Exercises. Well, vice versa, Tactical and Strategical Exercises, sorry. It's a deterministic model that incorporates many of the lessons learned in 1914 to 1918. Ship staying power is determined by the number of guns that each ship carried, and it's measured in shell hits, which are translated to an equivalent of 6-inch hits in the case of cruisers and 15-inch hits in the case of capital ships. The two systems, by the way, are completely incompatible with each other, which is a bit of a problem when simulating some of the battles. Gunnery is modeled in ideal conditions, and the umpires in the Royal Navy spirit that I was referring to earlier are expected to adjudicate on most of the penalties. And this is important because it means that we already know from the outset that this model is going to report higher rates of hitting than is historical, because it considers circumstances for gunnery that were simply not possible to reproduce in actual battle most of the time. Here you have a little sample from the tables that they used. Everything was reduced to 3 range bands, although the game did tell you that you could interpolate to your heart's content, which I did to get some more granularity. And there's many things that are not modeled. Speed and course changes are not important. Visibility conditions, as we mentioned, are not important. And armor penetration follows a very obnoxious all-or-nothing approach. Essentially, each hull class has a minimum caliber that can hurt it. Anything below that is not going to do anything. And I firmly believe that this is a way of weaseling out of the problem of converting between the 6-inch hits and 15-inch hits. What happens when a cruiser fires at a battleship? The game will tell you nothing, move right along. So the second game is a completely different kettle of fish. It's the Naval War College's 1922 maneuver rules. And compared to its contemporaries, it's a truly monumental effort of documentation. It goes into painstaking detail with no fewer than 53 individual circumstances affecting gunfire. Armor penetration is measured at different angles for different target sizes and aspects. It takes into account the angle of fall of shell at different ranges. It's simply superb. And the combination of all this is what the US Navy called the fire effect system, which is an extremely sophisticated mathematical device. The instructions on how to build a fire effect table are in excess of 60 pages. Full of formulas and equations, and I should know because I had to suffer through them to make my own tables for the simulation in many cases. The result is this. This is just a snippet from one of them. And there's not many things that the game leaves out. Guns smaller than 3 inches are not considered by the game. The fineries of fire control are not really taken into account either. It does consider director versus local control, but that's all. And funnily enough, deck penetration from plunging fire is not modeled in the 1922 rules. It was only added in the 1930 revision. It became very important for that one, in fact, because they started using it to compare battle line strength. And there was paper in the Northern Mariner or something like I think it might have been Professor Sim who made a paper suggesting that this information might have influenced battleship design decisions. And it had been instrumental in planning War Plan Orange. Anyway, these calculations are complicated enough that my tiny brain struggles with them, and working them out on paper certainly takes a while. So what I did was I created a computer simulation that would run the games for me. I used Python as a programming language. Python is great for fast prototyping and for trying things out. And it's also reasonably readable for non-programmers if the code is well structured. It's not the most efficient without resorting to some workarounds, but that's fine because even if the calculations are complicated to work out on paper, a mobile phone processor can do them in seconds, so that's all right. And all the source data is stored in external human readable files, which means that when I release the code in the near future, it will be easy for anyone, even someone who doesn't know how the program works, to make their own battles and play around with it. And both models run from the same data, so you don't have to work twice. Programmers are a lazy bunch. Here is an example of the output of the program, which looks a bit intimidating. I don't expect anybody to read through it. I'm just showing it to show you that it's very verbose and very detailed. And apart from that, it gives you some much more readable tables and nice, colorful charts that we're going to be looking at. Now, you may be wondering how we turn a battle into something workable for the program. Let's begin with the most critical information for gunnery and the one we began our session talking about, which is gunnery ranges. The problem with gunnery ranges is that written information in the battle is normally very fragmentary. So the most consistent source is the track charts produced by the participants in their official reports after the fact. So what I did was I scanned those charts and then I processed them with CAD software, with architecture software essentially, to measure ranges, angles, etc. Most of those measurements should be evident from the picture. That one in particular is a slice of the chase of HMS Kent to SMS Nuremberg in the Battle of the Falklands. From the charts, you can also kind of get speeds in that you can measure distances esteemed between timestamps. But there's a problem with that. The only thing you're getting is average speeds. And if you'll bear with a slightly technical and boring explanation for a bit, I think it's worth pointing out in case somebody wants to do it on their own. The problem with that is that we would be looking at the speed of a ship pretty much as the beams in the graph that you have on screen right now. Imagine a ship in the first beam going at a given speed, and then as it approaches the second beam, the speed skyrockets and it accelerates instantly to a much higher speed, which it keeps for a while, and then it breaks abruptly and goes down to a lower speed again. Now, that's obviously not good, especially since the Naval War College 1922 rules take acceleration and deceleration into account. So the most intuitive thing to do is to interpolate by drawing middle points in the beams and then joining them with a spline denoted by the blue line. But if you look at the middle beam, you will see that there's a little problem. Every point in the blue spline is actually under the average speed of the beam, which means that the data you're getting is completely wrong. Now, the way of fixing this is deforming the spline so that it preserves the mean. And that takes a skill in mathematics that I don't have. So I fished around and I ended up finding an algorithm that did this for me in a paper on atmospheric science written by a fine gentleman called Hedelius. And it took me a while to understand, but that's finally what I'm using. So now that we have seen how the ships move, let's look at how they fire for a bit. Guns were relatively straightforward, as both models assume that foreign guns are roughly equivalent to their own guns. And in the case of the Royal Navy simulation, most of the time when I wanted a German gun, I just went to the closest British equivalent. In the case of the Naval War College, there's a bit more nuance, and in many cases I had to come up with my own tables. There are some really modern and good methods for this. Bill Urens, again, has some fantastic papers on how to use computers to compile fantastic range tables for naval gunnery. The problem with those methods is that they were not actually available to naval officers in the 1920s. So I went creative and I went for the textbooks that they actually used. And the ones that were suggested by the Naval War College in the 1920s, which were the textbooks on exterior ballistics by Alger and Herman, and I followed the same procedures that they used so that my data would be consistent with the one that I already had for them. The same thing happened with armor penetration. Nathan Ocon is the resident expert in this case, and he has written very extensively on the subject. He has fantastic simulations written on it, but they are much more sophisticated than what people in the 1920s had. They instead used a variation of an empirical equation written by Jacob Damar, a French naval officer at the end of the 19th century, and they modified a couple of coefficients. So I took that equation, I took the Naval War College's coefficients, and I made my own tables. And this worked fine in almost every case. I say almost because both games consider side armor when talking about a ship's armor, and they measure it amidships. But there's a problem. The problem is that many protected cruisers of older design, such as Emden and Nuremberg, didn't have belt armor at all. Their armor scheme is more similar to the picture you see in the screen, with a sloping deck protecting the vitals and leaving pretty much everything else out. And this was a bit of a head scratcher. My first impulse was to check the Naval War College's data tables for similarly armored ships to see what they had done. And my mind immediately went to the Japanese Nitaka and Chikuma classes, which were very similarly built. So I checked how they had modeled them in the game, and the short answer is that they had modeled them completely wrong. In the first case, Nitaka was not given side armor at all, which is just ludicrous, because essentially a machine gun could go right through it. And in the case of Chikuma, somebody had written the wrong value in the side armor and gave it its conning tower armor value instead as belt armor, which resulted in a ship that was essentially unsinkable by equivalent ships or ships of similar displacement. So then I went for a different approach. I decided to take the thickness of the slope and to modify it by a factor of how much volume of the ship was actually left exposed. And the resulting figures were identical to the ones in the Admiralty Trilogy Group's games. Now, I'm not sure that they reached their figures using the same process, but the figures match, which is good enough for me. If there's something that I have learned over time as an amateur simulationist, is that any numbers that you get that agree with Chris Carlson's opinion are probably good. So now that I have knocked everybody out with an extremely boring introduction full of technicalities, let's go for the meat and potatoes of the presentation and talk about our case studies. They are not in chronological order. We begin with the Battle of Cocos, then we follow with the Falklands, and then we follow with Coronel. The reason I do that is that I think it makes more sense to talk about them in increasing order of complexity so that we can introduce elements of the simulation one by one. And there's an important disclaimer that will apply to the three. The disclaimer is that simulations stop when one of the side ships are considered to be firepower kills, when they are considered knocked out. And the concept of a firepower kill is not an easy concept to model, because it doesn't mean that the ship is sunk. The ship can still be shot at. It could even continue firing, even though it would not hit anything. And that means that the figures for ships that are destroyed are going to be slightly skewed, and we're going to have to do some creative analysis of them. There's a thesis written by Thomas Regan Beale of the Naval Postgraduate School in 1990 that also has a simulation of a number of naval battles from World War I and II, and he talks about the same issue much better than I could. So I also recommend going for that. Now, for the Battle of Cocos in the 9th of November, 1914, it's a single ship action, a very famous one, in the Indian Ocean between the Australian cruiser HMAS Sydney and the German cruiser SMS Emden, which had been detached from Maximilian von Spey's East Asia Squadron on commerce raiding duties. Emden was caught without full steam in the boilers, and missing around 50 people from her crew who had been dispatched in a landing party to wreck the Killing Islands wireless station. The two ships formed on roughly parallel courses northerly, and the first shot came from Emden at about 9:40, a surprising range of around 10,000 yards, which caught Sydney off guard as they didn't believe that German guns actually had that range. And not only they were firing at extreme range, but they fired very quickly and they fired very accurately, with the third salvo from Emden knocking out the Australian rangefinder. Sydney achieved no hits whatsoever for the first 10 minutes, and visibility started excellent by all accounts, but quickly deteriorated on account of smoke and spray. This is a chart from the 1921 Royal Navy simulation. The vertical axis is the staying power of the ships, measured in 6-inch hits, meaning that Emden is expected to be knocked out after about 40 of those, with Sydney being able to withstand around 64, 65. And as you can see, things go south very, very quickly for the Germans. She becomes a firepower kill just past the 40-minute mark. The curve is reasonably smooth, as very few factors are taken into account. Range and staying power are the only two things that the model considers. And that means that if the range were kept constant, the curve would be a perfect Lanchester curve, because the model would be a perfect Lanchester model, or Lanchestrian, if you want to give yourself some gravitas when talking about this. The Naval War College 1922 curve is a lot more satisfying to look at, and it's a lot more granular, even with a neat saddle point at the 14th impulse. Every impulse is 3 minutes, when the two ships change course abruptly and lose the range. And then in this one becomes a firepower kill at the 51-minute mark. And I have to say that my first conclusion was that the model seemed very solid in absolute terms, in that the outcome of the battle is the same as historical. By that, I mean not only that Emden lost. I would have been extremely surprised and a bit disappointed if Emden had won in the simulation, because it would mean there's something deeply, deeply wrong with my work. But also, the damage received by Sydney is very light, and that's very encouraging. In relative terms, however, the battle seems cut short. Now, this could simply mean what we mentioned before, that Emden became a firepower kill very early, but did not sink. And this is essentially what we're told happened. But there may be another effect in play, as we'll see in a second. These are the raw numbers. We're not going to read the charts because that would bore everyone to tears, but let's go for some highlights. This is data pertaining Emden only, and if you will look at the section that says hits scored, historically Emden hit Sydney between 14 and 15 times. And according to the simulations, this was 16.5 and 16.14 respectively, which is an absolutely monumentally fantastic fit. I was very, very surprised. Rate of fire is also modeled extremely well by Naval War College 1922 at around 2.58 shots per gun per minute, compared to the historical bracket of 2.44 to 3.33. So it falls slap bang in the middle, and that's really, really good. There are some tiny problems, however. First off, the number of shots fired by Emden is a tad low, perhaps. And this might be explained by the fact that, as we mentioned, battle should actually kept on going. And in the simulation, it doesn't. It stops abruptly because Emden can no longer fire. And this is not lunatic, consider the accounts that we have. Survivors from the deck personnel of Emden, when interviewed after the battle, report that as early as 10:40, that's 30 minutes before Emden beached herself in the North Killing Island, Emden's gunnery officer, a fine gentleman called Raide, was trying desperately to gather enough personnel to man 2 guns, but failed and could not get any significant volume of fire out anymore. And that means that she did indeed become a firepower kill very early. Now, if we were to extend the battle artificially, if we are to preserve the means, that means that Emden should have been firing monumentally fast at the start and abysmally slow at the end. And again, this is something that most reports agree with. According to the crew of Sydney, at the beginning of the action, Emden had as many as 3 salvos in the air. If you calculate the time of flight of a shell at that range, that means at least 1 shot per gun every 9 seconds, which is absolutely spectacular, and much more than the Naval War College would agree those guns could produce. And the accuracy was also reportedly insane, hitting Sydney in the 3rd salvo and scoring 14 to 15 hits in the first 10 minutes is truly impressive. So overall, I would say that the simulation especially the NWC 1922 one is remarkably close. That said, accuracy does seem somewhat overstated, and we'll talk about that in a bit. And here in Sydney, we do find two worrying discrepancies. One of them is that Sydney's rate of fire there is much, much higher in the simulation, in the US Navy simulation, than in reality. And that means that there should be something in the battle that would have kept her from firing as fast as she could. And it took me a while, but I eventually found a report by Gunnery Lieutenant Dennis Rayleigh, who said that he was deliberately firing very, very slowly and very carefully and trying to keep his crews from firing again until fall of shot could be spotted. This was standard procedure, really, but it could have been spurred by the fact that they did not have a rangefinder to work with after it was wrecked by the third salvo from Emden, which means that their guns would have been the rangefinders, so they could really not go into firing quick, independent fire without completely losing accuracy. So it's nice to see the model vindicated in that regard. And then the other discrepancy is that even though the model really well states that Sydney must have been around 16 times, must have been hit around 16 times on average, the damage sustained by Sydney is a little bit overstated. The Naval War College 1922 simulation says that 16 hits should have taken off around 15% of Sydney's fighting strength. And in reality, the damage she suffered was very light indeed. 4 crew members killed, 12 wounded, 1 rangefinder knocked out, 1 flash fire in the ready ammunition racks in one of the guns, but that did not knock the gun out. And other than that, basically no noticeable structural damage. And that leads us to think that the German shells must have been performing much worse than the model suggests. And then again, this is something that accounts confirm. The performance of German 4.1-inch or 10.5-centimeter shells was reportedly absolutely abysmal, with only 1 in 3 actually bursting. And their behavior was defined by Australian observers as extremely inconsistent, sometimes breaking up or exploding against very, very thin pieces of armor, and sometimes going through bulkheads without blowing up. So what are our conclusions from this, our first simulation? Well, first off, the simulated accuracy figures are very much in line with fleet battle experience. Fleet actions of the era typically had accuracy figures of between 2 and 3%. There's a very good article by David Isby in Strategy and Tactics in 1975, giving some of these numbers. But it's obvious that cruiser actions were different and not particularly well understood by the model. The high range rates, the smoke interference, spray interference, zigzagging and chasing the salvos, etc., are simply not modeled well enough. And that means that the expectations of a naval officer having trained with similar models and then going into battle at Cocos would have been shattered. In fact, Dennis Rayleigh was quoted as saying that nothing in their training could have prepared him for the extremely difficult gunnery conditions that he faced in that battle. And he was particularly surprised by the extreme rates of change in range experience. So in this case, when we talk about the mean expected outcome, the word mean is doing extremely heavy lifting here, because what we're doing with this model is trying to find a communion between the beginning of the battle, in which rate of fire was furious and accuracy was pinpoint, and the rest of the battle that quickly degenerated into a smoke-confused circus. On the subject of smoke, I forgot to mention that another thing that could explain the low rate of fire attained by Sydney in the battle is that she actually lost sight of Emden completely at 2 points in the action. And the only reason I have not modeled that is that, unfortunately, I have not found a single account explaining exactly when this happened, and I did not want to pollute the simulation with my own assumptions. So suffice it to say that the simulation does exaggerate the rate of fire that Sydney had, but that was expected. And finally, we do find some mathematical confirmation that German shells did underperform, at least early in the war, and especially the lower calibers. So it's good. It's something that we knew from first-hand accounts, but something that we did not really have a quantitative crutch to fall back onto. With this, we move on to the Battle of the Falklands, and we're talking about the 8th of December, 1914. And shortly after, the Battle of Coronel, Maximilian von Spee's East Asia Squadron attempted a raid on Stanley Harbour and was driven away by the guns from HMS Canopus. The battlecruisers Inflexible and Invincible sank Scharnhorst and Gneisenau, and the light forces gave chase to the German light cruisers. And we will be concentrating on the slice of the action in which Kent chased after Nuremberg. This was a hot chase for 45 minutes in mist and worsening visibility. In the process, Nuremberg burst 3 boilers and her speed went down to 14 knots. After 45 minutes, she just gave up trying to escape, turned to port, and engaged her full broadside, and it became a close action after that. During the chase, Kent was only hit once, and Nuremberg was only hit twice. And surprisingly enough, in the model, the close action does not actually happen. Nuremberg is destroyed during the chase, which is extremely disappointing. Well, actually, they do have 5 minutes of close action there, but that's about it. Kent only fires a few ranging shots at the beginning. That's why the German line is horizontal at first. And survivors claimed, again, that the German 10.5s actually outranged the British 6-inch guns, which also explains why in this chart the British are not hitting for a while. We will get into this later, but notice the absolutely ridiculous difference in staying power between Kent and Nuremberg. This is a bit of an artifact from the Royal Navy 1921 rules. Remember that they attribute staying power based on the number of guns carried by a ship, and the Monmouth class did have an absolutely ridiculous amount of guns. So they are credited with more staying power than probably they should have. The Naval War College 1922 chart is a lot more interesting to look at. The staying power difference is a lot smaller here. But the result is similar. The action finishes at 48 minutes, and Nuremberg's fire is completely ineffective after minute 42. Now, in both cases, I firmly believe that the possibility of reliably hitting a target at the extreme range of visibility during a chase is greatly exaggerated by the simulation. And it's funny because the Naval War College 1922 rules do account for bad visibility, but it seems that not enough. Let's look at the actual figures. There is a little to unpack in here, but the results of NWC 1922 are very close indeed in absolute terms. The number of hits scored, for one, is fantastic. Historically, Kent was hit 38 times, according to the NWC 42.25 average, which is great. Rate of fire is not that bad. There is a difference, but it's not a huge one. And do bear in mind that we do not actually know how many shells Nuremberg really fired. We know that she still had 1,100 shells left after Coronel. The figure given by Raeder in the official history of the German Navy is 110 per gun. It's extremely unlikely that she will have fired all of them in the action, though. And it's interesting because that means that in this case, the model is giving us a reasonable assumption of a figure we don't actually have. So I do think that this figure of around 700 shells fired is very interesting to look at. Now, accuracy is also overstated in the model, but we have already talked about that. Then in the case of the data pertaining Kent, damage sustained by Kent is again overstated. She was hit about the same number of times in the simulation as historically, but by the Naval War College 1922 model, she should have lost 20% of her fighting power. And that's simply not true. Casemate A3 caught fire, and that was that. There were 4 dead and 12 wounded, but all other damage was reported as very slight in the official report. The official report is in the National Archives at Kew. The document is ADM 137304. And that document mentions that other than that one shell, all the rest did essentially nothing. They also mention that most is the word that they use, most German shells failed to burst. So once again, we see that the model tells us something very interesting, which is that German shells, especially the German shell fuses of the 10.5 centimeter SK guns, were faulty in many aspects. And what the Royal Navy was reporting, that they were failing to burst, seems confirmed by the Naval War College that assumes they should have burst a lot more. So what can we learn from this one? Visibility is modeled correctly, surprisingly. There's some very complex tables in the game to calculate the range limit. And if you enter the latitude and the time of year and the time of day of the action, they do give you the visibility limit that the reports indicate. The problem is that it does not take into account how difficult it was to spot the fall of shot. the model seems to put too much faith on rangefinders, when in reality, especially at the beginning of the war, without seeing where your shells were landing, it was actually very difficult to correct your fire. And this is a fascinating discussion that we're not going to get into today for lack of time, but there's a number of excellent articles in the USNI proceedings in the 1910s and 1920s discussing the relative merits of spotting versus range finding and range keeping, and they're absolutely great. But I do think that in these actions, the inability to spot the fall of shot did play a serious part. The game also does not model the worsening, and I quote, visibility conditions during the action. It begins with a given visibility, and that sticks for the rest of the battle. And in this particular case, mist and rain did get in the way, and the model does not take that into account. And of course, our happy conclusion about the German shells underperforming. Just because I can, and because I have a simulation model and I can do whatever I want with it, I decided to model the battle after the chase was finished. And Kent would have fired another 225 shells. Nuremberg would have got another 125 in, and the action would have lasted another 9 minutes. Is that reasonable? It is. In fact, barely 10 minutes into the close action, according to reports, at around 6 o'clock, Nuremberg was on fire, and all of her guns were silent, but two, according to German survivors. So that means that, again, the combined models tell a much more accurate picture. Accuracy might seem a bit exaggerated, but do remember that we were talking about very, very close ranges in this case, once the chase was done with. And those figures are actually in line with the destruction of Blücher at very close range in the Battle of the Dogger Bank. So I'm also happy with those results. And now we go for the main course of the presentation, which is the Battle of Coronel in the 1st of November 1914. Really the first one we should have looked at chronologically, but this one has a bit more to talk about. During its escape from the growing pressure in the Pacific Ocean, von Spey's squadron encountered a weaker British force led by Admiral Christopher Cradock off the coast of Coronel in Chile, and the unequal engagement that followed will be remembered as one of the Royal Navy's darkest days in World War I. We're not going to go into the discussion of why Cradock actually engaged and whether she should have, etc. It's not a historian's place to judge, and a lot has been written about that by people who know a lot more than I. We're instead going to focus on the battle, and the outline is that both fleets formed roughly converging lines. They were firing on their opposites, with Scharnhorst firing on Good Hope, Gneisenau firing on Monmouth, and then the light cruisers involved had a bit of a battle of their own, with very little interference with the big boys. AMC Otranto was also in the area, and in fact, many of the reports that we have on the British side come from her, with most of them actually coming from HMS Glasgow. Unfortunately, Good Hope and Monmouth went down with all hands, and we have nothing from them. The first shot was fired at around 7 o'clock. The sun was setting, and it was silhouetting the British line against the horizon. Visibility was falling steadily, and rough seas interfered with British gunnery. The British line was to the leeward, particularly interfering with the casemates, and especially the lower ones. There's a lot written about the very poor design of the Monmouth and Drake classes. In fact, I think it was Fisher who mentioned that Sir White designed the Drake class or the Monmouth class and forgot the guns. So there's that. They were outdated ships, and they had no business being there in front of their modern German counterparts. This is the chart produced by the Royal Navy 1921 simulation, and the first thing that I find fascinating is that there is a very, very small difference in staying power between the two, in fact with a bit of an edge for the British, which is explained by this artifact that I mentioned of British ships having an inordinate number of guns, the ships of this class, and having an exaggerated staying power. But I do find this chart absolutely fascinating, and the reason that I do is that the Royal Navy 1921 rules model nothing of what has been argued as the decisive reasons why Cradock lost. Low visibility is not taken into account. Unequal crew training is not taken into account. Rough seas, not taken into account. Sun silhouetting, not a factor. And in spite of that, the British lose. And they lose resoundingly. And that's an interesting conclusion in itself, which is that, of course, all these factors were important, but they were not in any way decisive. there was no way, according to the Royal Navy 1921 simulation, that the British could have won, even in ideal gunnery conditions. However, if we look at a per-ship report using the same rules, we do see that Scharnhorst suffers quite a lot from the two heavy guns, the two 9.2-inch guns on HMS Good Hope, losing as much as 1/3 of her fighting strength. And that is very interesting too. First, let's point out that a battle means nothing without an operational context and a strategic context. And even though this would have been a tactical victory for the Germans, suffering a 33% reduction in firepower on Scharnhorst, away from a friendly port and with no way of repairing or rearming, would have been disastrous operationally. This would have been a very, very different event from the one that actually happened at Coronel. But that said, yes, that means, number one, the British lost, and there was very little they could do about it. But also, something must have happened that impaired their gunnery especially, because this result is much better than it should have been. So let's look at what the Naval War College has to say about that. And that is a lot more interesting. I think I have skipped a slide. Yeah, there we go. That's it. The Naval War College 1922 rules do give us a much, much better picture. As you can see, well, the British lose again, but German damage is much milder. This is very close to the historical outcome. Damage to the German ships is minimal. The simulation does take other factors into account, as we saw. And if we look at the per ship report, it is Gneisenau that has a rougher time, and that's historical. The simulation attributes this to Monmouth having a single caliber battery that has an easier time targeting in the difficult gunnery conditions in the action. British staying power has a bit of a plateau, as you can see at around 1940, which is when they get too far from the Germans and they lose sight of each other because of poor visibility, and then the Germans veer closer and regain their targets. And this also happened historically at least once. So I was very impressed to see that modeled by the Naval War College rules. Overall, this is a much more satisfying simulation with much more to talk about. If we go into the numbers, here we can see first the dramatic consequences of the ideal gunnery conditions, especially on poor Scharnhorst, suffering 34% reduction to her fighting power. She's hit by the Naval War College rules only 1.52 times, very close to the 2 hits historical. There is the slight annoyance there that at least one of the hits is claimed to have been from Glasgow, which was not included in the simulation for a variety of reasons. But it's still very, very close. Hits scored remarkably close as well, between 30 and 40 scored on Good Hope historically, 30.14 according to the simulation, 31.33 according to the British one. And the one thing that is a bit odd there, rate of fire is slightly understated in the simulation. This does make sense. The Germans were firing, again, stupid fast in this particular battle. And one of the reasons they did that is that they took all the crew from the disengaged side, from the casemates, and shifted them over to the other side to help loading. And then the accuracy is also a bit exaggerated. Now, I'm not exactly sure why that is. One possibility would be that, again, the model is exaggerating accuracy in general, but I'm toying with another idea. And the other idea is that the only information that we have on the hits that they scored on Good Hope, remember that we don't have any official damage reports because the ship sank, is from what the Germans could observe at the extreme limit of visibility. And there's a big uncertainty there. They said that they scored between 30 and 40 hits, which is a pretty wide range right there. So I have the theory that perhaps, well, one, they did not spot all of the hits. And two, they might have been biased and spotted mostly the ones from the main battery, which must have been easier to spot, not only because they were bigger, but because they were grouped nicely into broadsides. And if we only take those into account, then the accuracy, the theoretical accuracy from the historical scenario shoots up to between 7.1 and 9.4%, which is much closer to what the simulation says. The data for Gneisenau is not quite as good. Gneisenau is hit more in both simulations, about twice as much. And that the reason seems to have been that the Naval War College 1922 rules and the instructions 1921 both let the lower casemates of Monmouth, the lower casemates of HMS Monmouth to fire in extremely rough sea conditions. And we know from German accounts that they could not spot a single coherent broadside by those guns. And they were convinced, in fact, that the rough seas had the gun ports completely closed for the majority of the action. So there may be that. In any case, we have very little to go with in this case because there's honestly not a lot of information referring exclusively to Gneisenau. And since the figures are similar to the ones in Scharnhorst, I have no immediate reason to doubt them. The battle data for Good Hope, as was the case with the Germans, the number of hits taken is really well modeled. We see again the exaggerated accuracy of the 9.2s in the Royal Navy simulation. And I would like to draw attention to the very low rate of fire given by the Naval War College 1922 model, which is only 0.4 shots per minute. And the reason for this is that the Naval War College 1922 model models something called battery interference, which is that when guns of different calibers are firing at the same target, it becomes very difficult to spot shells falling. And the only way of compensating for that is firing slower. And this seems to have been a problem for HMS Good Hope. And I find it very interesting that it's actually shown by the simulation. We know that the 9.2s were only firing one shot in 50 seconds at the beginning, and that one of them was knocked out entirely in pretty much the first salvo from Scharnhorst. So that extremely low rate of fire seems historical indeed. And in the case of Monmouth, well, almost no data exists on what Monmouth actually did during the action, other than what Glasgow could observe from her sort of second row position in the battle. The Naval War College model credits her with a higher rate of fire than Good Hope. As I mentioned earlier, due to her single caliber battery, we're told by German sources that this should have been much, much smaller. So what can we learn from Coronel? First, the gunnery conditions were indeed abysmal, and they were indeed much, much worse for the British. The battle fits the Naval War College 1922 model very, very well in almost all aspects. And to me, that says that gunnery between two opposing, almost parallel lines was overall very, very well understood, whereas cruiser warfare, not so much. And if you look at gunnery tests conducted by the British in the years after the war, mostly in 1918 and 1919, they seem to have struggled with those lessons. And when they draw their conclusions from their firing tests, they seem to be extremely optimistic about what their guns could do in spite of the experience from the war. And there was a flurry of gunnery orders given by the Admiralty during the war, changing tack frequently and trying to find a solution. And something tells me that they did not quite find a satisfactory one, even by the end of the war. We also see that material conditions were obviously against the British, but they are not enough to explain the outcome. When I ran the simulation without the effect of the setting sun silhouetting the British line, the impact was minimal. And that's interesting in itself as well, because it does show us that, I mean, it's a very romantic thing to mention in a battle account, but it seems that the US Navy did not think this was such a big factor. And something that I find extremely interesting too is that the Naval War College 1922 model does not take crew quality into account at all. Now, much has been said about the reservist crews that the British armored cruisers had in this battle, many of whom had never been inside a gun turret before. And this is tragic, of course, and a very sad thing to think about when one considers what must have been going through Craddock's mind. But I like that the Naval War College 1922 model strongly suggests that even a very good crew would have been at a loss as to what to do. So I would conclude that the model hints that there was nothing much that the British could have done given the operational and strategic circumstances. So what can we learn from the simulations as a whole? Well, first, I find that the battle outcome matches the simulation outcome very, very frequently, and that's great. But that gunnery conditions in cruiser warfare are extremely difficult. The rapid changes in range, the fast rates of fire, resulting in smoke and gas interference, high explosive and lead shells resulting in fires and even more smoke, they're simply not well understood by the models, and they're such a chaotic environment that it's very, very difficult to quantify. We learn that German fire was indeed faster and very accurate, especially at the beginning of the actions, and much more so than the Naval War College expected mean would suggest. But we also know that it slackened very, very quickly. And I find it incredible that a war game can highlight those differences in fire doctrines, and they can actually be seen by the numbers. Then, spotting the fall of shot seems to have been very important, and the battles in which visibility was not great are the ones that exaggerate accuracy much more than the rest. And then we also have our little confirmation, of which I'm very proud, that the German 10.5 shells were absolute rubbish. Higher calibers were much, much more reliable. And what can we learn philosophically from the whole thing? My first conclusion is that wargames are living documents. They are much more than just numbers, and they should be studied in the same way that literature is studied or that cinema is studied. They not only give you facts, they also give you the understanding that people of the era had on how warfare should be conducted. And they even give you the aesthetic ideas that they had in their physical components. They give you the philosophies that they had, as we saw in the opposing views, or at least contrasting views, between the Royal Navy and the US Navy on how the chain of command should work. They inform you of procedures. They tell you what they wanted to rehearse more. They tell you what they thought they had down pat. They tell you if they reacted to the environment quickly or if they tended to follow antiquated and hidebound tactics. So they're superb. And I think no historical study is entirely complete without looking at historical wargames. I also found that historical simulation and modeling are valuable tools. At least I learned a lot by doing this that I probably wouldn't have learned if I had just read about the battles. And I think that it can help bridge the gap between purely narrative history and purely technical analysis that goes for pages and pages on minute differences in armor and muzzle velocities without looking at the big picture. I think this technique is particularly helpful when you have very few data points available. And I think that in that regard, naval warfare is a very rich environment for this sort of thing. And then, well, simulation using wargames can expose doubts that people had, can enrich the narrative. Technical documents have an air of infallibility to them. And when we look at them, we tend to think about naval warfare as something that was established. And the truth is that everybody was finding their way and sort of braving the weather. And I find it fascinating that they were just making things up as they went. We go full circle to Lieutenant Castle's game. At least, and if nothing else, simulation and wargaming make us think very scientifically and make us be very serious about the studies that we do. So where do we go from here? Well, just do more battles. The first two are almost done. I have marked Coronel as done. Yay! I have to do the rest of the Falklands. I have to do the Dogger Bank, which I find extremely scary and imposing. And maybe later we could be looking at some armed merchant cruisers, but the lack of guns smaller than 3 inches is problematic, and I will have to wrap my brain around that. And of course, when I get my conclusions, I will get back to you. The last thing that I would like to point out is that when I was giving the figures, let me backtrack a little bit. In the tables in the presentation, in case you keep the video, there are some numbers in parentheses, and those are the sources where you can find the historical information. And here at the end of the presentation, we have the sources for the Cocos figures. So just pause the video if you want to dig into them. These would be the sources for the Falklands figures, and these would be the sources for the Coronel figures. There's many more, of course, but this should be a nice starter. So I would like to thank everybody very much for braving this extremely long-winded talk, and I would be very happy to fumble through your questions, if there are any.
All right, thank you so much for the presentation. We do have a couple of questions here.
All right.
First one was a little bit long, so I tried to kind of distill it down, but Mark, please just jump in if I misrepresent it at all. So he says, I believe you were planning to move up from these single ship-to-ship engagements to larger squadron and fleet engagements. How would you model the combat for this, given that the ships have more targeting decisions to make?
Right, that's an absolutely fantastic question from Mark Flanagan. I have given this quite a bit of thought, in fact, and because of this, I had to come up with a couple of systems. The problem with the simulation is that I really do not want to project any tactical decisions on the model that the officers of the era, which were much better informed than I am, would have considered. So my approach was that in the last iteration of my model, I have given every ship a list of target priorities so that if one of the ships is knocked out, they know which one to move on next. And in the case of Coronel, this was very, very simple because it was 2 versus 2. So, if one of your targets is knocked out, just move on to the next one. In the case of something bigger, like Dogger Bank, there's another decision to make, which is in the Naval War College 1922 rules, if you switch fire to an adjacent target in the line, you get penalized less than if you switch to one that is very far away. So my logic would be to switch to an adjacent target first. But fortunately, with the system that I introduced, in which you can just write the names in order and run the simulation again, I suppose that the only approach would be to begin with the most reasonable decision and then to run all of them. But you are completely correct. The problem with that is that we would be projecting our tactical decisions a posteriori on the officers. And the only work around that is to consider all the possible outcomes and talk about all of them. But that's a very, very astute observation. So thank you very much for that, Mark, if that answered your question. Let me read the rest. A collection of battle line of red and blue turrets. Yes, I remember that article. That's brilliant. Yeah, very, very good. I remember having a blast reading it. And then there's something about AI there. Are you thinking of introducing any rule-based AI? Not immediately, but if I do, thankfully I have David Burden for that. David Burden is our resident AI expert, bots for each ship. That would be interesting, but I would be inclined, in fact, as you mentioned, to go for human players first. I suppose we could go for some people in the Naval War College to give us some input and give us their reasons. And I still think that will have a slight more reliability than AI would have. But then I welcome David Burden to disagree with me as much as he wants. So thank you very much, Mark, for the question. And if I missed anything, you have my contact details and I'll be delighted to discuss it with you. And yes, absolutely fantastic article, by the way. I loved reading it.
All right, and you probably said this in the chat already, but last question was, are there any explanatory design notes for the British and US rules?
Yes, there are some. Well, more for the US Navy rules than for the British ones. If you want some insight on the design of the Royal Navy rules, you're probably going to find more in Toby Ewing's work because it builds up on the various successive iterations of the model, and you can find how they went from one thing to another and roughly why. But in the case of the Naval War College model, not only there are design notes, but every year at the end of the Naval War College course, they published the discussions they had had about the games that they ran and the suggestions for rule amendments. And those were incorporated year after year in the model, which I found absolutely fascinating. You can have a year-by-year breakdown, not only of which rules changed, but who suggested them and after what game. So it's superb. I will be very happy to share those documents with you. And then, apart from that, in the Royal Navy models, as we mentioned, there are some notes in the official documents. We have done this because of that and because of that, but they are not plentiful. And I suppose this can be explained because the umpire was expected to give you the reasons for most of it.
All right, awesome. Those are all the questions that we had in the chat. Thank you so much again for the presentation. And I think that wraps it up for today, unless anybody has anything else. All right, sounds like no. But thank you so
Okay.
much again. You
No,
guys are all good to go.
no, thank you. And thanks everybody for attending and for some of the fantastic questions that we got. And I hope this wasn't too long.
All good, right on time. Ended right at 1. Just had the,
Excellent.
few extra
Well,
questions.
thank you very much for having me. It was an absolute pleasure.
Yep, absolutely. All right, I'm gonna go ahead and stop recording here.